Hello, Maddie. All right. Oh, I guess backgrounds. Maddie, you don't get to vote. I'm sorry.
I can't read it.
I don't get that. You don't get it?
No.
Ever listened to a really popular song by Queen?
No, yeah, why is it by Galileo?
Thunderbolt of lightning, very, very bright.
I understand the song.
Galileo, Galileo,
okay.
Galileo.
I didn't understand the song. I didn't know.
Oh, nothing.
I'm gonna vote for this one.
Vote. 2 votes, 3 votes. Not enough votes because some people suck. All right.
Because people have an idea of perfection that cannot be reached.
Well, the other part of this is not fair is that this particular set of backgrounds is not meant for a general population. It's meant for my own personal interests. And I brought you into this particular fold to let you vote on something. It's technically not up to you, but whatever. All right. I got 1 vote. Anybody else? Okay. Who cares? Votes? 1.
I like the Starbucks symbol in the top left. I like the little picture in the top left of it. It's
Treelick? Really? Okay. All right, Maddie, this is the background. You just spent 1 minute and 30 seconds watching us choose this background. All right. And I've got the hiccups, apparently.
you can hold your breath.
Nah, I'm good.
You guys excited about the 2 methods? I'm excited.
Saw the one she was like, yeah, guys, just 2 methods go.
Oh, I didn't prep this like I should have. Aaron guys doing Six Flags stuff. Okay, so I'm gonna stumble through certain parts.
One of the things, so that was really fun to learn.
All right, so algebra. You are on forces. Everybody's on forces, but algebra. You're in chapter 4. Calculus. This is on actually chapters 5 and 6, but it's stuff that we're relatively used to. So. Let's go. Click and slideshow from the beginning. The laws of motion, description of motion include position, velocity, and acceleration. That was kinematics. No consideration in kinematics is paid to what influences that motion, what causes it. 2 main factors need to be addressed and answer the question about why an ocean will change. What is the forces on the object and what is the mass of the object? Basically meaning what is the cause of that motion and what is the resistance to that particular motion. As we have now gone through pretty much the gamut of physics, all through the entire book, you see that equation pop up all the time. Voltage is the cause, resistance is the resistance, current is the effect. Cause is force, resistance is mass, effect is acceleration. I know there's more, but they elude me right now. Dynamics studies the cause of motion, and we'll start with 3 basic laws of motion, of which you know. They're going to go quick. Hey, there's Sir Isaac Newton. Got kind of a girly haircut right there, but that's, I don't know. Anyway, he invented calculus, which I love, is like a 3rd line in a list of everything that he did. But forms the basic laws of mechanics, Newton's 3 laws, forms the universal law of gravitation, so big G m1 m2 over r squared is also him. Invented calculus, that's him. And many observations that don't look like in optics. I'm going to get my clicker so I don't have to keep turning around all the time. Keep moving. All right. Cool. All right, force. Force is an everyday. It's a standard push. You guys got this. I'm not moving. Classic definitions. Usually when people talk about forces at the very beginning, they don't typically do what I did for you last year, which is describe the 4 fundamental forces from the very beginning. I personally like this because I think the gross oversimplification of this is vastly too annoying. So usually what most textbooks will do is they will split forces up into contact forces and field forces, one that have to be pushed on and one that have to be doing through empty space. When the truth is every single force is actually a field force. For example, I lay my hand on the table. What fundamental force is actually pressing up on my hand? Electromagnetism. But what do we call it typically when doing force diagrams? Force normal. So that's the difference. They would technically say we're doing this. Hey, force normal is a contact force and force electromagnetism is a field force, when in all actuality they're the exact same thing. So if you do see this on your homework, you will see things like A and B and C all represented as contact forces, when in all actuality, all three of those are really electromagnetism, where all three on the bottom are representing field forces of, you have, let's say gravitation, and then you have electric, and then you have magnetism. And of course, we know that E and F are, of course, combined together in electromagnetism. Fundamental forces, there they are. We've talked about all of these in greater detail, so we're not going to do it now. More about forces. Springs are your best bet to calculate force. Why? It has to do with the linear possibility of a spring, and how we'll talk a little bit more in depth about this. Shoot, why not now? Okay, so here's a spring in a nutshell. Maddie, I'm doing an example on the board. I'm sorry. All right. I put a post on the board. I put some spring on said post, and I hang a known mass from it. What we already have this sitting out. What do we got here? We got 100 grams. We know how to calculate that because it's the force of gravity. Then what we can do is we can measure. This is too strong a strain to notice this, but let's get a weaker spring for the sake of being able to notice it a little bit easier. All right. So you can mark where a string, of course, has nothing on it, and basically, obviously, that means zero force. You hang some string from it. I don't think this is going to be enough. That's what it is. Let's do more. Here, this would be 100 grams. Hang it on there. Mark again. Put another 100 grams on. Mark again. And what you will notice consistently as I put more and more 100 grams on is that it always takes the exact same distance for the most part. It might be a little bit off. That one's definitely a little bit off. Or was that 100? That was 100. Is that 100? Pretty consistently. So, to that end, do we need some fancy mathematical formula to tell us what it's going to do? No, we know exactly what it's going to do. We have it essentially right here. Okay, let's go. How do we get force of gravity? It's mass 0.1 kilograms times 9.8. So roughly 0.98 newtons. Or let's roughly go, hey, that's 1 newton, that's 2 newtons, that's 3 newtons, and that's 4 newtons. And then, of course, you can take everything off of there. This is just a reference. And I can start pulling it on myself. And now, even though I cannot feel how much force is in my fingers, as I pull right here, you can tell me exactly how much force I'm pulling with my fingers. It's roughly 2.5-ish, based on the bottom of that, but that's not the important part. Okay, so springs, they just they noticed from proper scientific technique of just, hey, freaking look around and see what happens, that we can nicely make this scale, and so that's why we use them all over the place. Of course, we'll talk about the actual model of it a little bit later on. Hello? You just coming on in? All right, so springs are always used to calculate force for that particular reason, and as long as you have a reference frame, you pretty much use that there, because doubling the force doubles the reading on that. Let's move on. See ya. Nature of forces. Forces are applied perpendicularly to each other. Here it is. Force is a vector, so it has an x component and a y component. Moving on. Newton's first law. You should already know what Newton's first law is. All forces balanced, or no forces means it's at a constant velocity, or if you want to state it from the very beginning, all objects will travel at a constant velocity until acted on by an unbalanced force is typically what is said. But I don't like that worded in a way that seems more Newton's second law than first. So all objects will traveling at a constant velocity as long as their forces are balanced or there are zero forces. The other way to say that, of course, is that at zero acceleration, they're going to have balanced forces, also known as the law of inertia. But why is it weird that inertia is in this particular? It does need to be called law of inertia, but why is it weird that the first law is called inertia?
Because you don't notice it until it's
Because you don't notice it, until it changes, until acceleration actually happens. Meaning, if I throw a tennis ball and a bowling ball, I saw it.
Okay.
Yeah.
Sure. That's
So
Monday.
yeah, just test one. You already got it. Sorry, I don't want to reiterate what you already know. Inertial reference frames. Okay, this is kind of a little bit of a different thing, and not too much. We call an inertial reference frame a constant velocity. Okay. Non-inertial reference frames is quite simply when an object accelerates. And we always try to do our force diagrams from an inertial reference frame, because from a non-inertial reference frame, fictitious forces potentially appear. We should probably have a little bit of time at the end of this, because I don't think this will take me the full time. I could be wrong on that. I apologize if I am. But there's this really cool video about this guy that is in a non-inertial reference frame. And to put in perspective of a non-inertial reference frame, you know a car going around a curve. Okay? From our frame of reference outside the car, it is non-inertial, and we can see everything that is happening. But to an individual in a car, a fictitious force appears. Okay? Meaning, if you are sitting in the car, what fictitious force, or what does it seem like happens?
you
Push to the side. Many people call that the centrifugal force. We know that is not an actual force. That is a fictitious force that results as the properties of inertia, because the object wants to stay going straight, so it appears to go to the outside. So inside there's this fake force that occurs. In other words, in a non-inertial reference frame, you can get kind of these fake forces, these things that are not real, which is why we always try to make it sure it's in an inertial reference frame. Also what? You can see it on the board right now. I regularly told you when dealing with torques and rotational stuff that you can place your fulcrum whatever you want as long as it's not accelerating. And the basic thing there, without getting into too much detail, was simply that I just want your frame to be inertial and not non-inertial, because that can mess and cause weird perspective things to occur. Let's see if I'm missing anything else. Nope, we're good. So what's an inertial reference frame? Constant velocity, yeah. You're looking at it from a constant velocity. Newton's first law, alternate statement. This is exactly what I said before. This is just talking about the forces at the same time. Balanced forces or absent forces tell us no force on an object, no accelerations on an object. Can't conclude that an isolated object is either at rest or moving at a constant velocity, or they really could have just said moving at a constant velocity. First law allows the definition for force as that which causes a change to motion, inertia, and mass. It's that same sort of thing before. What we see is that this ratio between mass and two masses is the inverse relationship to acceleration. Meaning, if I double the mass, I expect acceleration to cut in half, which is what brings us to put it on the bottom half of Newton's second law equation. You knew all this already. Mass, it's measured in kg, but what is it actually measuring? Amount of matter, correct. If you remember last year, I told you a fake definition. I said that at least for the beginning part, I can say that, hey, it's the amount of atoms in an object. Why is, after the conversations that we've already had, why is that absolutely an incorrect statement? Not quite what I was going for. You're not entirely wrong, but you wouldn't think from that perspective unless you start to get up into like nuclear physics or potentially into, it's not necessarily. Why is it just in more basic sense? Why is it wrong to say that the mass is the number of atoms in an object?
That's small speed up.
What's that? Nope.
Atoms have matter.
They do.
That's hard to calculate.
Nope. Yes, it is hard to calculate, but that's not why it's an incorrect sentence. Why is an incorrect sentence to say mass is directly equated to how many atoms are in an object? You're sitting in front of you with two objects, both that have the same mass. Do they inherently have the exact same number of atoms inside them? No. Atoms have different masses. So probably a better bet, but still slightly off due to the reasons that Matt just said, is that it's the number of nucleons in an object. But then you start to get into when you've got that many electrons, it does mess with the numbers a little bit, at least 3 or 4 decimal places down the line. So a very generic answer is mass is the amount of matter in an object, which is confusing to your most students because like they don't understand what mass is and they don't understand what matter is. So how the heck can I understand either one? So ultimately, it's how much stuff. It's how much stuff there is. But yeah, the measurement of stuff, as it were. All right, mass and weight. Are mass and weight the same thing? I get very irritated if you would have said yes. For example, if we take 2 objects with 2 kilograms and put one on the moon and put one on Earth, do they have the same weight? No, because what is weight actually? Force of gravity, yep. And why is the force of gravity on the moon less than it is here on Earth? Moon has less mass. It is so nice to run through these conversations that take me like 20 minutes each and just kind of like say that and you guys say the answers back. So I really appreciate doing this. It's mostly about me right now. Anyway, so there we go. Algebraically, Newton's second law. Acceleration. More force will get you more acceleration. More mass gets you less acceleration. Typically, it's worded like this. So there it is. Newton's second law. You guys have used it 1,000 times. Now, an interesting thing about this is you will notice in this particular case the proportionality symbol. Okay. We scientifically measure this as, hey, put more force into something, see what happens. Put more mass into something. What is interesting about this equation is that there isn't a presence of a constant, okay? That acceleration has a 1-to-1 ratio with this particular ratio over here. Force divided by mass is not acceleration. Force causes mass and acceleration, and mass, and it resists acceleration. But acceleration, sorry, I said that poorly. Force causes acceleration, mass resists acceleration. The reason there's a 1-to-1 ratio, though, really comes down to this equation right here and the definition of the Newton itself. What is a Newton? A Newton is however much force, however much oomph it takes to cause 1 kilogram of mass to accelerate at 1 meter per second squared. Off of that simple definition, without even looking up here, you can start to get like, oh, well, what if I wanted to accelerate 1 kilogram at 9.8 meters per second squared? Well, if 1 Newton is what it takes to make 1 kilogram go at 1 meter per second squared, to get 1 kilogram to go at 9.8 meters per second squared, it takes 9.8 newtons, and thus our definition of weight, right? Weight is what it takes, what it takes to accelerate something at the gravitational constant of g, which of course is different from amounts of mass. Clicker, or not. I just had it. It's in my pocket? No? All right, whatever. I'll find it probably. Moving on. More about second law. You can split it into the x and y. It's a net force. You guys have messed all this before. You're going to see this in notes. There's the conversation about force. Pound. I don't think I talked about this last time. Regularly, if you got pounds before, I would have you convert them to newtons. I would still strongly suggest that roughly that's the case, or the more exact amount, I would not write this rough figure down. The exact amount is that 1 pound is equal to 4.45 newtons. So I would regularly suggest that you go to newtons and mess with stuff. But just in case you didn't know this already, the pound is defined as the slug foot per second squared. Slug being the technical American unit for mass, although used at almost no places that most of you are looking at me with the face of, I've never heard this before in my life. For that exact reason, nobody ever uses it. Everybody pretty much uses pounds. It's weird that they use pounds. Like in America, if you talk to like a generic person, they will know pounds of force, and they will probably know kilograms of mass, even if they don't exactly know that it is directly connected to mass. They will have heard pounds, they will have heard kilograms, but they will have never heard slug before. And then there's feet per second squared, which is this unit for acceleration. Gravitational force conversation we had before. I think the one I did, the one I explained last year is simply this. Here it is again, real fast. You drop somebody off of the side of a building. The only force acting on them is force of gravity. How much will they accelerate? 9.8 or g. So if the only force on them is f of g, we know they will accelerate at g. In other words, that's the necessary oomph to get something to accelerate at 9.8 meters per second squared. But if that person is standing on the building, how much will they accelerate? 0. That being said, did f of g change size? No, their mass hasn't changed. They're at a different spot of Earth. So we use a trick to basically imagine every single person is dropped off the side of a building to measure their weight. And we use that even if they're not dropped off the side of a building because it 100% works. Or you can remember our conversation that we talked about that what G actually is gravitational field and the ratio between force, gravity, and mass. And then that equation makes really good sense because it's just a redistribution of these particular constants. Gravitational field is the number of newtons per kilogram multiplied by kilograms, of course, will tell you newtons. Gravitational field is set up by the planet that you were particularly standing on. Moving on. More about weight. Varies with location because it's force of gravity. Can be extended to other planets, but of course G will change from planet to planet. You'll remember, of course, this conversation. This conversation that force of gravity is equal to mg, and then later this year I told you, of course, force of gravity. Last year actually, I told you is equal to this, r squared. And so I said if those equations are the same, then if this is mass of object and this is mass of object, then G must be equal to this mass right here. Thus, little g is equal to big G times mass of planet over the distance to that particular spot squared, which is usually the radius of that planet. Weight's not an inherent property of an object. Yep, it can change from place to place to place. Kilogram is not a unit of weight. Hey, they only say it once. This is the equivalence that they'll usually hear. Most people that know that equivalence have probably been in the weight room once or twice because that's usually the ways to measure weights is in pounds, which is a correct measurement of force, and kilograms, which is not a correct measurement of force. The reason why that is the equivalent and only valid on Earth is this. The correct conversion from pounds, let's pick something like 80 pounds, here on Earth is to go over to newtons, and 1 pound previously stated is 4.45 newtons. So how many newtons is that? $80 times 4.45.
356.
356, cool. 356 newtons. That is the force of gravity. If you have the force of gravity, what do you do to go figure out its mass? Divide by G. Or in other words, you multiplied by 4.45 and you divided by G, which is about 9.8. What is 9.8 divided by 4.45? Do that real quick. 2.2. There's the conversion right there. So why does this conversion not work on other planets? Yeah, G is not the same on other planets, and thus it doesn't work for those places, which is why I suggest learning this particular methodology right here. Moving on. Gravitational mass versus inertial mass. I told you that gravity has two properties. It's true. It is a little bit strange for science as we've continued on. We typically treat them differently. We'll call them gravitational mass and inertial mass to reference their two properties. One being, what's gravitational mass? All mass attracts all other mass. All mass has gravity. And inertial mass, all mass goes at the same velocity. What is strange to us is that they essentially are the same amount. Now, this strangeness somewhat gets rectified or understood when you get into general relativity and understand that inertial mass and gravitational mass are exactly the same from two entirely different perspectives. Weirdly non-inertial reference frames, which is why we're not going to mess around with it too much right now. But it's strange to us that they are in fact the same. In other words, here is the equation that contains inertial mass. Here is the equation that contains gravitational mass. More mass gives us more gravity, and more mass gives us more acceleration. Scientists say it's strange that when you plug this guy in here, you get this equation. And you have two different forms of mass up there. It is weird that they cancel out, that there is no transitional factor whatsoever, in which case the acceleration, when there's only force of gravity on the object, is in fact G. That's a little bit strange because they are two different properties, but luckily for us, it kind of works out nicely in our favor. All right, so moving on. Yeah, experiments have shown gravitational mass and inertial mass have the exact same value. Third law, for every force, there's an equal and opposite force. You guys have heard this 1,000 times before. My new favorite example for third law is as follows. Spainauer can take a piece of paper and swing at it right now. And I don't have to worry too much. I know, proper form. I know you're all scared. It's okay. I do not have to worry about breaking my hand. How come?
Because it can only put a small amount of force on you.
Why?
Because you only put a small amount of force on you.
Why? You're 100% right so far. Just keep going. Why can I only put a small amount of mass on it? Force on it.
A lot of mass.
Therefore,
Same on.
it doesn't have very much inertia. Therefore, it accelerates very, very, very easily. And I do not need much force to make that happen. And Newton's third law says the amount of force that I put into it is the exact amount of force it's going to put back on my hand. So in order to cause that piece of paper to break my hand, what would have to be incredibly, incredibly large past my human possibility? My causing of acceleration. I would have to cause an insane acceleration, which would amp up the force that was necessary, which would amp up the force back on my hand. On other terms, if I go over and punch the wall over there, okay, why will I more than likely very easily break my hand with not needing very much acceleration at all? That has a huge amount of mass, and therefore it takes an incredibly large amount of force to accelerate it at all, which it does accelerate a little bit in that case, but then can put that incredible large amount of force back on my hand and break my hand in that particular process. Notation, as was stated last year, if it says force AB, that is force of A on B. Good note then is the second letter is always the object you've drawn the force diagram on, right? So if I have this mass sitting on the table, of course force gravity is down, but every single force that you list in the simple form can be traded out for the two objects in question. Force gravity, what are the two objects? So how would you write the force gravity on this differently then? This would be the force of?
Earth on
Mass, or whatever you want to call it. Very good. And then typically you'd say force normal is up. How would you reword that in this particular notation? Force of table on mass. Point being, you'll notice mass was the second thing in both cases. The second letter is whatever the object is particularly on for absolutely all of them. Moving on. Trying to see if I need to spend too much time on this. First action force, the other reaction force. It doesn't matter which one's considered which. Nope, and I think we're good. Action reaction examples. I mean, this is, I'll give you my favorite. I think I've done this one before. Bullet recoil. Okay. Whenever you fire a gun, there's a chemical reaction inside that which expands gas incredibly fast. Or in other words, you can say there's a force of gun on bullet. What must be the case then? Bullet on gun, correct? And thus the reason for rifle recoil. If you put a force to even take a small mass like that piece of paper, but if I accelerate it incredibly, incredibly, incredibly fast, it's going to have a large force on it going that way. And according to Newton's third law, if you put an incredibly large force on the bullet going that way, the exact opposite way, you have the exact same force back on the gun itself. This is why it's somewhat dangerous to make guns that are smaller in size. Or another way to say that is inherently what's going to be more accurate, a rifle or a handgun? Rifle, just because it is more massive. If you want to look it up, I will tell you, I looked up a bunch of examples of Newton's third law to try to show to people in class, not necessarily this year. And it's hard to find one without a ridiculous amount of expletives on the back end of that. But I will tell you, one of my personal favorites was a woman who was holding a Desert Eagle, or a 50 caliber gun, okay? And that 50 caliber bullet, by the way, caliber by itself does not inherently mean it's a big boom. But what naturally usually comes with 50 cal is an incredibly large amount of gunpowder on the back part of the bullet. So that large amount of gunpowder, that's ultimately what brings big boom. So you hear like 9mm versus 50 cal, you automatically think, oh, 50 cal is because it's bigger. That's why there's a bigger boom. No. It's because there's more gunpowder packed on the backside. Put just as much gunpowder on the backside of a 9mm, and that's going to have some major impact, nearly as much. But it's not, actually, that would be a little bit unwieldy. So it's got a 50 cal, basically, but she's holding it very loosely with a hand. And of course, it comes back and just slaps her directly in the face, and she uses expletives, and it's hilarious and all that. Moving on. Action-reaction pair. This is what I said before. This is the object sitting on the table right now. What's the action-reaction pair of force of gravity here? No. That's the pitfall. We said it's not the case. Remember what I said last year, and it's this. Force reaction pairs cannot exist on the same force diagram. Must be on separate force diagrams. 2, they got to be the same fundamental force. Are gravity and normal even the same force? No. So what is, don't go so quick, again, to do this correctly, what you do is if I say what's the equal and opposite of force of gravity, you go, okay, what's force of gravity actually? What did we say earlier? What's force of gravity actually? What are the 2 objects in question? Earth on mass. So, if there's a force of Earth on mass pulling it down, then the third is there's a mass on the Earth pulling it up. Why does it have way more an impact on this mass than it does on Earth? The mass of Earth has ridiculously large inertia. What is the equal and opposite of force normal on this mass? No, the one you're about to do is the force normal. Force of table on mass is the force normal. Mass on table, correct, pushing this table down. That's what my students are in Physics 1 right now are currently having to deal with as far as like those rotational stuff right up there. Or if you'll remember, I did this last year. My goodness, I'm just losing everything. I lost the clicker. There it is. Okay. There was a bridge with the bunny, and I had this whole conversation about how, yes, you can use force of gravity to calculate how much force the bunny is putting on the bridge, but that's not force of gravity. Meaning, if you did a force of the bunny, what's the force diagram on the bunny? Force gravity and force normal up. Instead of normal, I'm going to say this is force of, oh crap, bridge on wabbit. It's not a bunny anymore, it's a wabbit. I do this every year. Okay, why are those 2 equal? Which law means those 2 are equal? No, first. What about that situation says those 2 are going to be equal? It's a constant velocity, correct. Then, because there is a force of bunny on bridge on wabbit, there is a force of wabbit on bridge. So, is force of wabbit on bridge the same as gravity? Amount-wise, yes. Is it the same thing? No. What fundamental force is this actually?
Electrons.
Yes, it's the electrons in the bottom of the foot of the bunny pressing down on the electrons of the bridge. What simple thing could that bunny do that would make it that force gravity is definitely not equal to the force of wabbit on bridge? Accelerate. Let themselves jump up or jump down. I mean, and you know this, right? Because if you have ever like sat on, like just goofingly as a kid or even as an adult, stood on a scale in the bathroom and jumped up and down, what do you notice happen to the numbers as you're jumping up and down? They bounce up and down. Does that mean your gravity is actually changing during that time? No, that's not what it's actually measuring. Moving on. Free body diagram, that's a little bit of a joke to kind of have you guys do at this particular point in time. So if you struggle with that, what do we got here? When the rope is attached to it, it's got, literally it's pretty easy stuff here. Equilibrium, basically just following Newton's first. All the forces are balanced, all the forces are equal to 0. So here's an equilibrium example, boom, not that hard. I'm not gonna make you go through it. Analysis. Newton's second law example. One of the freaking easiest problems that you guys have ever seen. So I'm not going to mess around with it right now, unless you really want me to, but I don't think that you do. Okay. Note about force normal. Normal does not have to be equal to force gravity. You guys know this, and you can see over here someone pushing down on the book. Normal is what I always call a reactionary force. It's the electrons and electrons pushing, but what you always want to do in a force diagram is pretty much draw absolutely everything first before force normal, because that's kind of what decides how much force normal is going to be. Problem solving hints, we've done all these 1,000 times before. Yeah, let's have you do this one real quick. Yeah, let's take a little bit of time and have you guys do this one real quick. Let's say that the mass, you've got angles there. Let's go. I don't know. Are they going to put numbers? They're not going to put numbers. Or maybe they are. I don't know. Nope, they're not. Here, let's just make it dumb. Let's go. Weight of the stoplight is going to be 20 newtons. Calculate the tension in all 3 cables. I don't think we did anything directly like this last year. We did something, a simple version of this, but not the exact thing.
Bring the picture back with the gills.
Oh, sorry. Sorry, yeah. Am I going the wrong way? I'm going the wrong way. There you go. So we'll say force of gravity of this guy, as I said, 20 newtons. And the question is, calculate the tension in every cable. I will give you twice as long as it takes me. Once I find a pen. All right, you got 2 minutes and 30 seconds. Two equations, two unknowns, right? You get the answer?
I think so.
What you got?
I got 14.3, 19, and 20.
What's that?
14.3, 19, and 20.
The correct answer is 12.04, 15.97, and 20.
Oh, that's right. So how I get that without
Well, you can somewhat cheat this particular system because it's a nice triangle. It is the ratio of a triangle. It's a 3, 4, 5. So you are going to have a ratio of 3, 4, and 5. So, to get to 5, 20, factor of 4. So the others are up by a factor of 4 as well. 3 being 12, 4 being 16.
That's not bad. I mean, I did sign. Like I figured it was.
Basic trig functions.
Oops.
You did 20 sine 37,
There you go. Here's your 2 equations, 2 unknowns. Dink, dink. Solve for T1 up here, plug it in down there, get T3, substitute back in, and you're all set. Yes.
Can I write?
Sure.
That was the direction that I was going after. But
What'd you do differently?
the first thing I did, but I still got the right answers. I just said 20 sine 37 is T1, and then 20 sine 53 is 15 is T2, which is 15. Okay.
You said what now?
No, I heard you wrong when you were talking about the forces and the ropes.
Gotcha.
Whenever you said that the answers were, that was wrong.
Yeah, the answer is T1. Oops, sorry. Yeah, sure. T1 should be 12.04.
Yeah, I got that.
T2 should be 15.97.
Okay, so I did get those, but all I did was 20 sine 37 and 20 sine 53. And I know that was the wrong concept, but it was apparently the right.
So I think, shoot, why does that work? All right, so that works, I think, in this case because there's 3, and I think what it ends up being is that if you shift the axis, if you shifted the axis to like right here, yeah, that's exactly what it is. If you shift the axis to right here, then T2 has to equal T3 specifically in the Y. So T2 would be T3, 20 newtons times cosine of, what would it be? Cosine of 37 degrees, and the other one would be sine of 37 degrees. So I think that works out nicely because there's only 3 cables up here, but highly suggest you get used to this particular methodology in solving these type of problems.
I realized that the way I did it wasn't the way that actually made sense for the problem when you started doing it.
I mean, I usually don't, and honestly, at this point in time, you're in physics too. I mean, you understand hopefully a lot of this stuff. So if you can kind of work it out in a backwards way and it's easier, absolutely, do that. Like if I would have noticed that ahead of time, I would suggest, yeah, sure. But obviously, if it shortcomes you potentially in the future, just make sure you learn this other possible methodology. Any questions about what I did there? Relatively straightforward once you see.
I pretty much did the exact same thing, just got different answers. I just solved for T2 instead of T1 and plugged
I
in.
mean, you should get the
Are
exact
you in
same
radians or degrees?
I'm in degrees.
Yeah, well, yeah. I mean, we can talk about specifics here a little bit later on, but I do want to try to try to get through this stuff as much as possible. All right. You've done inclined planes. Shift the axis. Shift the axis in what direction? Towards acceleration. Correct. Multiple objects. You've been messing around already with those specifically. This is the Atwood machine. It's just basically a thing on two particular types of pulleys. If you don't consider the wheel, I have to remind you of this because we actually flipped it with the Atwood machine later in the chapter. If you don't consider the wheel or you assume the wheel has no impact on the system, which we will in this chapter, you can go ahead and assume that these two tensions are exactly the same. You'll remember us talking about it a little bit later on, that those two are actually not the same. Good night. Come on, Debbie. Those two are not the same. Also, as it's suggesting up here, make sure with multiple objects, particularly when it comes to that worksheet. Oh, I totally forgot how I said I was gonna make that worksheet easier. Here's what I decided to do to make that worksheet easier, okay, that I gave you. I didn't like thinking about it yesterday. I was driving around and I was like, that's so stupid to make them be redundant and redundant and redundant and redundant. So here's what you're gonna do on that worksheet. So it's not nearly as ridiculously redundant. On all the odd numbers, 1 through 9, 10 and 11 are their own thing. On the odd numbers 1 through 9, you are to remember. You just pretend there's friction on them. Basically, odd numbers, do part B, assume there's friction. Even numbers, go ahead and just ignore friction. You're not doing A and B on everything. You're literally just doing B for 1 through 9 odd, and you're doing A for that way. Basically, you're doing like half the extra work. Hopefully, I got to you before too many of you got too deep into that worksheet. But if not, I apologize. Atwood machine. All right. Just like, this is exactly what you're dealing with on that worksheet, so I'm not going to spend too much time on this, but there it is. What I would suggest when you're dealing with something like, for example, the problem that looks like this, where there are two potential different angles, is once again, just set this as being your positive. Now, as I'm doing that, obviously you're going to be shifting the axis, and that would make sense for being positive in this case anyway. And then the y is kept kind of independent from that. Like the y, obviously, on this one is going to be this way, and it's going to be that way over on that particular guy right there. But I think you guys are probably pretty good. What are you doing? All right.
So you're keeping that drawing.
Force of friction. What is friction actually? Electromagnetism. Specifically in surface friction, it's the interaction between electrons and protons, correct. Yes. We'll talk about, yes, and you have to deal with static friction and kinetic friction, so let's talk real quick. When is it kinetic friction? Be more specific. I will give you an example of static friction while it's moving so that you can get an idea. I'm currently holding on to this guy right here, right? I get going.
When it's moving.
And then I stop.
Relative to the surface.
There's what I'm looking for, yes. When the two surfaces are moving relative to one another. That, of course, particularly gets important when you start talking about wheels, an advanced topic of wheels, because an object can be moving and still deal with static friction because they are not moving relative to each other. Or, dealing in relativity here, if they are technically going the same velocity, that means they are zero to each other. Yes? In other words, you and the drink in your car, okay? Sitting on you decided not to put it in the cup holder. You're putting it on just that little in-between ledge right there. Can the car actually keep it going the way it needs to? Yes, because of static friction. When you take off and that drink is sitting there on there, you're not paying attention to it. It can, of course, go right along with your car. Which way does static friction go in that case? No, not opposite of velocity. Because it actually goes the same direction as velocity. All right, here's your car. You're facing forward, right? You got your drink right here, or here, even better. All right, I've got an object holding on right here, and I take off. Which way did static friction on this just go? That's the thing that actually accelerated it. So which way does static friction go?
Away from inertia.
Opposite of the way the object sort of wants to go. Correct. Inertia, he wants it to keep it stopped, and therefore friction was forward. Or in the case of you've got a big heavy thing in your trunk, or in the back bed of a truck, or on my hand right now, and it's already going, and I stop, velocity is still that way, but in this case acceleration was back, because inertia wanted to take it forward, static friction pulled it back, until it gets to its maximum. Remember that's why there's this less than equal to sign right here. How much does static friction apply? Quite frankly, it puts the necessary amount out, okay? Or, simplistically put, if I push on this mass right now with 2 newtons and it's not moving, then we know that static friction is the opposite way, the left at 2 newtons, right? Push it 3, 3, 4, 4, 5, 5 until I get to the maximum. If the maximum is 6 and I push it 7, of course, then it's going to break, and that means we're going to move over into kinetic friction. Kinetic friction is way simpler that we have found because basically it's just set equal. It's a constant amount depending on how you're moving. Questions, concerns? All right, I know that was a really quick rehash, but I think that a lot of this, of course, is going to come out in your homework and all the like, so I think that we're going to be good there. Okay, here. Let's talk about friction in a different capacity. Let's talk about air friction, okay? Or moving through a viscous medium. Or are they going to do that yet? They might talk about this later. This was surface friction, okay? Coefficients depend on the surface in contact. We already talked about static is generally greater than kinetic, generally opposite of the direction of motion for kinetic, or opposite of the way it wants to move, which I already talked about. Static friction. Boom, here is your picture like I drew last year. Okay, it's going to be 1 to 1, 1 to 1, 1 to 1 until you get to the maximum, and then of course it drops down into kinetic. Kinetic friction is going to be constant. It's going to be, I mean, you've seen this already before. I think you guys have already been using it, so I don't think it's a big deal. If a homework problem gives you 2 materials, it's a little bit weird to give you this table because to say like copper on steel is not to talk about a lot of things that affect that actual object, like the texture of that object, whether or not there's some material on the outside of that object. Like it could be copper, but there could be sticky on the bottom. Or I could be pushing my hand across the table and it's the same coefficient of kinetic friction until I get to like a sticky part because somebody dropped apple juice. So honestly, most coefficients of friction are found experimentally in a lab and then used as is necessary in that particular problem. But these do in fact give you kind of a rough idea where to start. Does it make sense that glass on glass has a relatively high coefficient of friction relative to wood on wood? Well, if you've ever tried to slide 2 glass planes next to each other compared to 2 pieces of wood next to each other, you're going to find it a lot easier to do the wood on the wood, that type of thing. Or, you know, you get ice on ice. Kind of makes sense that it's a very low number. Or, for our sake, it's ridiculously awesome that, I'm not going to pronounce that correctly, synovial joints in humans is ridiculously low and kept that way with liquids and all sorts of other anatomical situations. But it's a really good thing that the coefficient of our bones, in fact, is lower. Now, it kind of makes sense. Who probably has a lower coefficient of friction in their joints? Younger humans or older humans? Younger, because older humans have a tendency of using their joints and moving around and running them into things and getting other stuff on there and putting stuff in that particular spot. So coefficient of joints goes up, and that leads to, of course, older humans complaining about their joints being sore and the like. Of course, they're probably going to do that when they have had a lot of velocity, like an older human, 37 years old, that plays basketball on a Thursday night and now walking around on a Friday is a little bit stiff and the shoulders moving on. Okay. Again, all these friction examples you guys have done before, so I'm not going to mess around. I mean, it's just literally, look, this is what you are dealing with right now, so I'll talk about it very, very briefly. But this is like a problem that you could have totally on that worksheet. We have a force pulled up and to the right. It's going to accelerate to the right. This mass is going to go upwards. Obviously, it wouldn't naturally do that without this particular force diagram. Tension's bigger than this force gravity. Notice that they labeled this force gravity with its different mass because obviously it's taking force gravity. And then over here, you'd sum the forces in the y. What would the sum of forces in the y be? Well, there'd be normal plus force in the y minus force gravity in the y, and that would be equal to 0 because there's 0 acceleration in the y. Normal here, bigger or less than force of gravity? Smaller because? There's another force helping in the y, and we know they're balanced equal to 0 because it's not accelerating. Moving on. Oh, no, we're not. Moving on. Done with chapter 5. Chapter 6. You will note on chapter 5, you did not mess around at all with calculus in the slightest. Now, chapter 6. Circular motion. We've already talked about circular motion last chapter. That's, of course, when it goes around in circles. But to calculus, you're still going to have to deal with circular motion now. Algebra, you'll notice there were not any homework problems with circular motion with your stuff, nor were they on the test. That's because your book does not cover them yet. It will cover them again in circular motion in chapter 7 when it gets a little bit more in depth for them. All right. Moving on. Uniform circular motion. There's the equation we dealt with last time. Okay, how are they bringing out uniform circular motion? And there's conical pendulum. Just basically mean this is the tetherball example right there, and it's kind of trying to get you to see like, hey, what force is causing circular motion right here? More specifically,
The tension up into the center of its motion.
which would be which tension?
Oh,
Tension in the x. Yeah, tension in the x. Remember that it points towards the center of the circle, which is directly that way, which, yeah, would in fact be tension in the x. And in this case, you'll notice that x goes with sine because, of course, where the angle is positioned, and that's the most logical place to put that particular guy right there. All right, so this is just giving you examples of what you're going to see on these particular homework assignments. Horizontal flat curve, we've messed with this stuff before. If you wanted me to go through these problems, I think we're going to see it enough on the homework, but I want to try not to mess with this too much. It's weird to put banked curve and then they don't actually bank it on this particular guy. So this would be the force diagram specifically if it's on a flat surface. Now, one thing that I don't love about this particular thing, it took me forever to figure out even as a teacher. It's like, wait a minute, why the heck does force static go left? Well, I mean, I know that it has to go left in order to cause a circle, so we could use that and just say it does go perpendicular, but why? What's causing it? Well, here's the easy thing. What is actually causing your car to change direction?
The wheels turning.
The wheels. If you're at this particular spot, your wheels probably look something like this. So my struggle, that's very, what's way too sharp, but my struggle with that is, wait, what the heck? Because that's not actually towards the center. It's not pointing that way. Which way are those wheels actually pointing friction? Right here. Force of static friction they're talking about here is literally just this right here component of that particular force. Let me draw that in a more correct direction. There it is. There is the force of static friction. This is just the perpendicular component to there. Why does there have to be a parallel component of static friction at the same time? You're driving around in a normal car.
Because like that would just mean your wheels would just.
Let me say this differently. To go in a car at a constant velocity, you're just traveling down the road. Forget the wheel. Simple stuff. What's force diagram?
Ballast. Or gravity.
Gravity.
Normal.
Normal.
Engines. That's it.
Nope.
Engine.
It's moving.
Oh, so engine.
We would say engine on car typically, but actually it's not the engine on the car. It's the engine on the wheels. And the wheels, what force is it of the wheels that's actually causing this to go forward? Force of friction, static. But according to this force diagram, what is the object going to do? Why doesn't it accelerate in a standard capacity? Because there is typically air friction back in an equal amount. So I reiterate my question. Why is this there parallel? And when I say parallel, I mean parallel to the car. Why is there a parallel force in this scenario to keep you going around the corner at a constant velocity?
Continue to move.
No, because you're counterbalancing air friction that's back. This component is literally just balancing out that. Typically, what we do in these problems is ignore air friction. Thus, we ignore the wheels pressing forward like this and just pay attention to the wheels going that way, even though they're doing both at the same time. Does that make sense? Okay, another heads up. Here's a banked curve. A banked curve, in your particular perspective, basically you're just going to take, it's like a car on an incline. You view it from the back perspective, in which case, if we were 100% accurate, I know it's a little bit of a steep curve. Okay, if we were 100% accurate, what forces should be on this banked curve? Gravity, sure.
Normal and angle. And then like friction going up.
So there's an interesting thing about static friction, okay? Remember that with static friction, because that's what we're dealing with this maximum situation. Have you ever gone around a corner too fast? If you're ever going around a corner too fast, you will find your car drifting in what direction? Towards the outside. So standard way that forced friction is going to go is absolutely the opposite of that, towards the center. However, on the opposite side of things, what you will notice is that when you go around a curve, there's actually a wide range of speeds that you can go around, as opposed to like an orbit, there's a very specific speed for a very specific orbit. Or let's put it like this. If this curve was made of like ice, the iciest ice that has ever iced, is there a very specific speed for a very specific spot on that curve? Yes. The fact that it's not ice and that it is road means that this friction can actually point different directions. Or in other words, if you're going too fast on the icy one, you're definitely going that way, which would mean that friction points in. But what if you went too slow? If you went too slow, what would your car want to do? Go towards the inside, in which case technically forced static friction is out, back the opposite direction. All right, moving on. Ferris wheel, I mean, these are relatively simple problems. Main thing, once again, is just be careful with forced normal. A lot of people, like here, I'll give you Ferris wheel problem / Tarzan / hey, you're about to do some Six Flags South roller coaster problem going through the bottom of the roller coaster. They're all the same. In these cases, at the bottom, at the bottom, at the bottom, force diagram, force gravity is down, of course. But in this case, tension, this case, force normal. I think they're using normal over there. Should normal be greater, equal, or less than force of gravity? No. No. Centripetal acceleration points which way, guys? Towards the center of the circle. So in this particular case, the acceleration for this particular person needs to be going up, which means force normal, tension, or whatever needs to be greater. And that's what you see in this particular case. Or actually at the top of the path, which way do they need to be accelerating? Down, so force normal pressing up in this case needs to be less than force gravity. The big difference between the Ferris wheel and the roller coaster problem at the top of the path is what?
Like there's a track up there.
Sure, so you're right there.
So there's
The big difference between the Ferris wheel problem, this is what it looks like in the Ferris wheel problem at the very top, but does your force diagram for the roller coaster problem look exactly the same? No, why not? Nope.
well, there isn't a force normal up.
You're starting to get it.
The force normal is towards the center.
Force normal's down. The force normal is down in this particular case, not upward, due to the fact that twofold. One, obviously the track goes on top of you and presses down, and two, and much more importantly, I'm going to go ahead and guess on your Ferris wheel that you're definitely accelerating less than gravity, but not all that much because the Ferris wheel's not moving that incredibly fast. Yes, on the other hand, the roller coasters are going so fast that could they actually have force normal up? Not if they want to accelerate at more than g. Force gravity down will cause an acceleration of 1g. This force diagram will cause an acceleration of anywhere between 0 and less than 1g. What's necessary for force normal to go above 1g? Better be pressing the exact same way. Make sense? Ish? Am I being too simplistic? Do you guys have this already?
I'm picking up what you put.
Okay. Non-uniform circular motion, basically all you're going to see there is you're going to see forces, of course, act in the perpendicular and parallel at the same time, and pretty much what you're going to have to do is standard vector addition stuff in that particular case. Circular, non-uniform speed, I mean, I'll let you do the math on that. I'm not going to worry about it right now. See that? We talked about this earlier. Centrifugal force is not an actual force. We already talked about it, so I'm not going to go in again. Coriolis effect. All right. In the Coriolis effect, this is that video I was told you I was going to talk about at the very end. This is a non-inertial reference frame. If a person throws a ball from this spot right here, standard, and throws it straight, and the object's not moving, what's it going to do? Person's right here, and they throw it across. Which way is it going to go? Straight across. Of course it is. Now, is that still going to be the case when the thing is rotating? Yes, it is.
Yeah.
It's going to leave the person's hand and it's still going to go straight. But will it appear straight to the person on here? No, because while it is going straight, they're continuously curving, which means things appear to curve. Did they actually curve? Not from a non-inertial reference frame. Okay? From an inertial reference frame, they don't curve. From the non-inertial reference frame, we get what is the Coriolis force, the thing that makes it appear to go left. For example, if you fired an object right now, bullets, rocket, whatever, south, okay? If you just fired it straight south towards, I don't know what state's lower than us, some like Alabama or something? I don't know. I know Kentucky is. Sure, Kentucky, Tennessee, straight south, okay? And you were to, what's that?
You're missing that thing.
Are you really? No, it's south, right? No, I'm starting one now. I gotta see it.
Let's get the map up.
Let's bring on the map.
Straight south.
Kentucky is south of us.
From like
Yes?
Point.
Straight?
Not straight south, you're right. Neither is Tennessee either.
Yeah, Tennessee's way off. So that's
Yeah, it's off. It's off. I mean, not way off, but we're like the corner right there. It's close, but
it's like Arkansas.
Mississippi. There you go. Mississippi's pretty much straight south of us. If you were to track that object, okay, assuming that that object does not have any like onboard computer or systems to make sure it maintains south, what is that object going to appear to do as it heads south? Drift in a direction. Which direction? Discuss quickly in your group. We'll be right back after these messages.
So the sun's so if you shoot probably
Wait, we're saying like it's shoot south. She shot south.
no, it drift east. Okay.
There it is. That's what I wanted to potentially get to.
No, yeah, here,
We're real close. We're real close to getting that.
All right. What's it going to do?
Go west.
Drift west. Because
The world is turning east.
the world is turning east. So that's what's called the Coriolis effect. You see the Coriolis effect, we talked about this a little bit the other day when talking about the fact that Canada and England are on the exact same latitude. And that's weird because when you think in your head of what their general weather is, it does not match in the slightest. Most of us think of England as having at least somewhat similar temperatures to us who are further south. Why does England get warmer weather than Canada? That chilly water. That chilly water that results from the Coriolis effect. Which way does the water near the equator go due to the Coriolis effect? Just the same way as you said. It was going to go, hold on.
Well, it goes east.
Yeah, it's going with the ocean. Yeah, so it's going to the east, right? And then as it gets further up, it slows down, and so it slows down and heads west. Those general tendencies in the X have a direct effect then on the Y, and the thing going east, that warm water at the equator going east, then starts to drift upward to replace the water, so they get warm waters over in England. Same reason why California coast can be found in their general latitudes to be warmer than their other respective latitudes at the exact same spot. Okay, and yeah, Coriolis effect. There you go. We'll see a video of Coriolis effect in just a second. Another couple fictitious forces examples are, we get this sort of thing all the time. Okay, if I'm talking about an object in a train, okay, or if you will, you've experienced this if you have absolutely anything whatsoever hanging from your rear view mirror right now, okay, and the train specifically accelerates, not moves, accelerates forward, okay, what will that thing hanging from your window do? It'll appear to have a fictitious force pushing it back. Is there anything actually pushing it back? No, absolutely not. Why does it go back? The inertia of it wants to stay going at that same velocity, or another way to look at that is this. It needs that particular force in the X so that it also accelerates forward at the exact same acceleration as the object in question. So it fictitiously appears to go back. There's a really weird thing that occurs. Let's see if you can't figure out this right now. If I hang a tennis ball from the top of a ceiling in a van, it's going to do exactly what you're talking about right now. It's going to take that tennis ball. If I accelerate forward, it's going to fling backward. If I take that car in my van and turn hard to the right, that tennis ball is going to go hard to the left. But if instead of a tennis ball, I go to a local party store and pick up a balloon with helium in it, okay, and I attach that helium balloon to the bottom of the floor, it will do the exact opposite effect. Meaning, if I accelerate forward, the helium balloon will lean forward along with me. If I go left, that helium balloon will go left along with me. Discuss quickly in your group, why is that? I think this is the last slide we're going to do. Pretty sure. 22 to... Yeah, they're all the same. All right, man. I think I'm going to talk... Yeah, I'm going to talk with them in just a second, then we'll be all done. All right, what do you got? Why does that happen?
The air has inertia as it apparently goes that way.
You look at the wrong object when you think about the helium in the balloon. What you should think of is not the helium in the balloon, but the air surrounding the balloon. Why does a helium balloon float? Because it has less mass, essentially, than air. So, when we accelerate forward, it is not that the helium balloon is coming forward, but that the air in your car is going backwards, and then the helium just goes the opposite location. As you go left in your car, it is not that the helium balloon goes left, but that the air in your car goes right, and the helium, we'll show you that actually. I think there's a Six Flags thing that will do that the day of. All right, I am at 22. This, I'll tell you right where I am, because it's the last thing that I'm going to cover in here, but I'm going to spend another day on this because it is differential equations, and quite frankly, I want to let you guys use most of your time to kind of get, I'll probably give you guys a couple days in here. So there'll be a day on Monday. There'll be a Monday. Next Monday is going to be kind of a day for homework. Tuesday is going to be a lab. Wednesday, basically, we will hit this. Thursday is going to be your prep day for the test. And then I think that we have the break, and then your test is actually on the following Monday. Tuesday, when we're there. I promise not to be there on days that school doesn't exist. All right, questions, concerns on that? Fair enough. I'm going to show you that video, but we are done with new notes. In case Maddie wants to find it, I'll look it up while. Good point. Doing that, let's see here. I was trying to figure out the guy's name. Crap, I have to remember that. Let's go. Let's just go. See what happens when I type in non-inertial. Nope. It's all fancy people. Guy in spinning room.
I think we've seen a Tom Scott video.
There he is. Yep, that's about all yet.
Last video, I was at the...
Tom Scott. He's 6 minutes. All right. I'm not going to play this here, Maddie. You can look it up on your own. We'll talk to you later. Bye-bye.